Hey guys, welcome to Zach the Tutor, and today we're gonna talk about Williamson ether synthesis. So, this is a way to synthesize an ether from an alcohol and then an alkyl halide. So let me write the general formula for this reaction. Okay, so what happens here is that we get our first group with the alcohol, and then we put it in very, very basic conditions. So in a stronger base than sodium hydroxide or potassium hydroxide, we're talking about sodium amide, sodium hydride, etc. And then we get an alkoxide here, right? And then the second step of the reaction is the addition of an alkyl halide. So the Rx, and the X is anything that is a halide. So chlorine, except fluorine, because fluorine is weird. So chlorine, bromine, iodine. And then we get an ether right here. So let me write what you need for this reaction. So for the base, you need something really strong. We're talking about, let's say, sodium amide, right? Or sodium hydride, or even like a very, very good reducing agents, such as like sodium metal, potassium, that is a weird K, potassium metal, and lithium metal. And then for the, just to note, this reaction goes by the SN2 mechanism, right? So we're doing a backside attack here. For the alkyl halides, we need something that is in the primary position or maybe in the secondary position. What works best is in the primary position. So, because it's a backside attack and the alkoxide is a good nucleophile but also a very good strong base, it can, if it's greater than a secondary alkyl halide, so it's on, let's say this is a primary alkyl halide, and then a secondary alkyl halide would be on a carbon that's attached to two other carbons. If it's a tertiary alkyl halide, what it would do is that it would just do E2 mechanism and just eliminate and make a double bond instead of do a backside attack. So if you remember from the SN2 stuff, SN1 stuff, that whole spiel. Anyways, what you also need is that a really anhydrous conditions. So no water in the reaction, because since the alkoxide is a really strong base, what can the alkoxide do is that, that's a weird negative sign. What can the alkoxide do is attack the hydrogen from the water and pull it out to make you back your alcohol, and then plus OH minus. Because the alkoxide is even stronger than OH, this reaction is favorable. You can also not need to do the first reaction or the first step and just make not just make, but get a sodium alkoxide version of your alkoxide. So in a sense that if you want phenoxide, so this is phenol. If you want phenoxide, this is benzene with OH, it's called phenol. If you want phenoxide, you can either put it in a really strong basic conditions, or just get sodium phenoxide, which is a reagent you can like buy for a reaction. So you don't necessarily have to do the first step of the reaction. What else there is to know? I think those are primarily the main stuff. Phenol is kind of weird. You can pull out this proton and make an alkoxide or phenoxide out of it by just regular NaOH, but this is because the benzene ring can resonate that negative charge on the phenoxide. So just phenyl is a weird exception. Let's do a couple of examples just to show you how this reaction works, and so you can get a good grip on it. So what if we want to synthesize diethyl ether? So here's an ethyl, here's ethyl, two of them, diethyl ether, right? And we need these two reagents. So we need 2-carbon alcohol and a 2-carbon halide or alkyl halide, right? So to make this product, what we need to do is that we need to put the 2-carbon alcohol or ethanol in some very basic conditions. So we put it in sodium, not sodium because that doesn't make any sense. When you put it, is it sodium amide? So the sodium really doesn't do that much in this reaction, but the amide, with its very basic negative charge, will attack. Here, let me just draw the bond on here better. It'll attack the proton on the alcohol, kick it out into the oxygen, and it will give us our alkoxide, so full octet of electrons, and then plus, again, no sodium, and then this species right here. So the negative charge, it really doesn't like it be negative, because think about it, this is ammonia, and this is it's very stable, but when you remove a proton from it, it's actually incredibly unstable. We get our ethyl alkoxide and we get our ammonia species in solution. Now, the second step of this reaction, so here's first step, second step. The second step of this reaction is the addition of our alkyl halide, right? So we get our newly formed alkoxide or ethoxide, since methyl, ethyl, ethoxide, plus, and then we add mechanistically, so we add this into the reaction. So 1,2-ethyl bromide. What will happen is that it will perform a backside attack on this carbon, right? And then the bond between the carbon and the bromide will be kicked off, and then we will make our desired diethyl ether. Realistically, like in industry, this is not going to be the most common method, I think, because there are cheaper ways of making diethyl ether and not wasting precious sodium amide. Anyways, so we want to make this ether, so tert-butyl isopropyl ether. How are we going to do this? There's two ways if you think about it, or two logical answers. One is incorrect and one is correct. So let's do both and see what will happen. So the first one is we do our alcohol be our tert-butyl, plus we make our isopropyl group the alkyl halide. Let's make this iodine so we can switch it up, spice stuff up. Right here, bingo. And then what do? So for the first step, I keep writing pluses instead of 1. For the first step is that we put the tert-butyl alcohol in really basic conditions. And so, or let's do a reducing agent. So Na, then what will happen is that so we will get this sodium alkoxide species in solution. And when we do, we can do our second mechanistic step, which is add the isopropyl alkyl halide, right? Then what will happen is that, so add this, what will happen is that the really basic tert-butyl alkoxide will not attack the iodine, but will attack this carbon and then pop off the iodine, and then it will give us this product. However, since this is a really strong base, we will also get a little bit of propene, since it can do an E2 on this reaction. So we chose this to be this this alkyl halide, couldn't find the word. This alkyl halide, we chose it to be secondary alkyl halide. If we chose it to be the tert-butyl or a tertiary alkyl halide, what will happen is that we'll get, we'll get our isopropyl alkoxide, right? And what we'll do is that since it's a tertiary alkyl halide, it will just perform an E2. So the reaction would be will give us only this product. So 1, 2, 3, propene, 1, 2, 2 methyl propene. So you gotta be careful where that alkyl halide is. And usually your best course of option is to put the bulkier, tertiary group, not on the halide, but on the alkoxide. So right here. Anyways, that was it for this video. I hope it was short and simple. I'll try to leave practice questions that are probably not mine in the description. Apologies for the lower production quality. I forgot my battery charger for my camera. Thus, I had to revert to my phone. I hope there wasn't a noticeable quality degradation. If you guys have any questions, feel free to ask them in the comments. Thank you guys for your time. Good luck.